Assalamu alaikum everyone, welcome back to my channel. So in this video I'm going to discuss about two problems. One is 2.12 and the other is 2.26. So first of all, discussing this problem given here, you are given a simple circuit with two diodes, one battery source and a resistor. So first of all, the most important thing we do here is we see that these diodes are made up of silicons. So their value is 0.7 volts. And the next thing that is given that we have to determine V0, I1, ID1 and ID2. For that purpose, first of all, we'll find this I1 that is flowing through this first loop over here. To calculate that, we simply use KVL. After using KVL and resolving it into a simpler form, we get this equation, and solving this equation gives us I1. So after that, we know this current 28.18 milliampere current is present at this node, this particular node. Okay, then it has two main paths. One is for ID1 and the other is for ID2. As the resistance on both the sides is same, so we can say that this current will divide into two similar values. So simply dividing this current, we found I1 by 2 to calculate the current through diode 1 and the diode 2. By that we found that 14.09 milliampere is the current passing through this first diode and the second diode. As we have already calculated our three particular required things, that is ID1, ID2 and I1. The only thing left is V0. So as we know, V0 is parallel to these diodes and the voltage of the diode is 0.7. So the voltage in parallel is same. So we have already found V0 0.7, I1 that was 28.18 milliampere, ID1 and ID2 they both were 14.09 milliampere respectively. Coming to the next problem, it is related to Zener diode. Just a sec. So yeah, this example here is 2.26. We are given a circuit here and we are required to find VZ, VR, IZ, and we are given a load resistance of 3 kilo ohm. So first of all, let me give you a quick overview for such circuits. Whenever the voltage across the Zener diode is less than the voltage calculated after ignoring it for a while, if the voltage calculated is greater than the Zener diode, then the diode turns on. Otherwise, if the voltage calculated is less than the Zener diode will act as open. So first of all, ignoring this Zener diode and calculating the voltage across this closed circuit, we found that the voltage here was V is equal to 12 volts. So this 12 volts is greater than this 10 volts. So automatically this Zener diode is now on. As the Zener diode is on, now we can say that the voltage across this Zener diode and the voltage across this load resistance is same. How so? Because the voltage in parallel is same. So 10 volts here means 10 volts here. Now the next thing we are about to find is VR. VR is the voltage across this resistor. So basically to find this VR, we can first find current if we want to. How so? As we are given 16 volts from the source, this 16 volt will come to this node and this 10 volts will be over this node. So we can apply the current current division rule by 16 minus 10 divided by R. It gives us the current through this resistor. When we have the current, we can also measure the voltage as V is equal to IR, or like this. Okay, over here we have first solved for the voltage and calculated the voltage for this loop, for this resistor, sorry, and then we have calculated the current for this resistor. But we can also calculate the current first and then we can calculate this voltage. It won't be a big deal. As I told you, the principle for calculating this is, first of all, we do 16 minus 10 divided by this resistor. It gives the current across this resistor. Then using that current we can calculate the voltage as well, but I'll stick to the one written over here. It has said that VR is equal to VI minus VL is equal to 16 minus 10 is equal to 6 volts. Is simply given that the current that is initialized, that is supplied, is Vi, and the current across this diode is Vz. 16 minus 10 gives us 6 volts across this resistor. Then we found the current across the load resistor. How? So basically we were given uh, this load resistance of 3 kilo ohm in the question, and we know the Ohm's law is V is equal to IR. Now simplifying it for current, that is I is equal to V by R. We already calculated the voltage, that was 10 volts, because they both were in parallel, so the voltage over here is also 10 volts. Simply applying the Ohm's law, I is equal to V by R. 10 divided by 3 gives us the current across this particular load resistance. So calculating that gives us 3.33 milliampere. After that, calculating the current across this resistor R. For that we can use the same rule, that is Ohm's law. How? I is equal to V by R. Voltage across this resistor was 6 volts, and the current we are about to find is supposed to be calculated by dividing this voltage by its resistance, that is 1 kilo ohm. So using this simple Ohm's law, we get 6 milliampere. Sorry, 6 IR is 60 milliampere, because 6 volts divided by 1 kilo ohm is 6 milliampere. After that, we can also find the current through this Zener diode. How? You can simply say that the current through this resistor was 6 milliampere. So this current comes to this node, and it has two paths now. Applying KCL over here, so the current entering IR is equal to the current leaving IZ and IL. So simply applying KCL, we get IZ is equal to IR minus IL, and we get 6 minus 3.33 milliampere. That gives us 2.67 milliampere. After that, here he has calculated power across the Zener diode. As we know, the formula for power is P is equal to VI. So we have already calculated the voltage across this Zener diode, that is Vz, and the current across the Zener diode, that is Iz, 2.67. So multiplying this simply gives us the power. Although we were not asked to calculate this power, but still if you don't do that, it won't be a big deal. Now I'll show you the Proteus simulation of these circuits. Okay, over here. Yes, I performed this circuit in my university, and now I'm making this video in my hostel. So please bear it. I'll explain it in this photo, and I hope it will be clear to you. So in this circuit we have resistors. In this circuit we have resistors R1 and R2, and a diode with some battery source. You can also use a cell here, and to find these parts we simply go to the library. This part here is the library. We click on P. After that comes a search bar. In the search bar you can simply write the name of these diodes, the one that you are going to use in the circuit. Just use this like 1N4740A. When you type this, it will give the same diode that you are searching for. After that, for the resistors, you can simply write generic resistors, and this battery source, you can use a cell or a DC voltage source here. It won't be a big deal. Then there are there are these ampere ammeters. To use these ammeters, you have an option of meters over here. You click on this option of meters, and you will find a DC ammeter option over here. Use that in series with in throughout the circuit, because current is calculated in series. And the other circuit was this one. It has the same types of components like diodes, resistors, and battery source. The procedure to find these would also be the same. Like you will simply type this name of 1N4001 in the search bar after clicking the P option over this one P option. So DC ammeter is also given here. I'll show you this in a while. After that, clicking on the library and picking up these components, simply patch them in this schematic view. And for these meters, we have also attached a DC voltmeter here. So as I told you, click on this option over here, and then you will be shown this log over here. In this log, you have different options like oscilloscope, logic analyzer, counter timer, and so on. But the one which we are concerned with is DC ammeter and DC voltmeter. So we pick up DC ammeter and simply patch it in series, and for the DC voltmeter we patch it in parallel because the voltage is same in parallel and the current is same in series. So this was all for these two examples. Now I'll describe about the DC power supply in the next video. Hope you like this one, and do wait for the next one. I'll just upload it in a while. Thanks for watching and hope you have a good day.